Here we go. Start of the second unit. We're into talking about some new types of functions, which hopefully aren't terribly new. What we're really going to do is push towards exponential and logarithmic functions. And the impetus behind that is to look at this constant e, this number, and then compound interest. I suspect that you guys have seen some of this before, so make sure that you get whatever is new. Make sure you brush up on whatever you need to. But this is what we've got. If you haven't seen the number e before, this is what it is. 2.7182818, blah, 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 blah. And it keeps going on, and there's a whole bunch of interesting properties that you might recognize. Really, e is defined as one of these two limits. What you'll notice is that these limits are really the same thing. To go from one to the other, we just say n is equal to 1 over s. That way now, when n goes to infinity, s is going to 0, or you could say if s goes to 0, n goes to infinity, and you can notice now the 1 over n here turns into 1 over s, which is just s, and this n turns into 1 over s. Really, you could say that this, I'll put this back in green, this one here is like an s root of 1 plus s, and we're looking at a limit as s goes to 0. So we're looking at getting infinitely close to the 0th root of 1 plus something infinitely small. And over here, you can see kind of what's happening. Here we have 1 plus something infinitely small again, because n is going to infinity. So we saw that with the limits at infinity, the 1 over n is going to go to 0. But then we're multiplying it by itself an infinite number of times. Weird things happening. Strangely enough, this is what the limit converges to, this number, which again, maybe you've seen before, maybe not. It's got all the same kinds of properties as pi, where we've got this number where the decimal keeps going forever without any sort of pattern. It's an irrational number. It's a transcendental number. It's got all the cool properties, but we haven't seen it near as much as pi, and there's a really simple explanation for that. Pi shows up with circles. Circles, here, we look at the relationship between the circumference and the diameter, and we say circumference over diameter is equal to pi here. Cool. I remember learning this in middle school because we could do little types of geometry things that young. E doesn't show up until much later in the math curriculum for most of us. And the reason is because it mostly shows up in this compound interest. Some people maybe see some of this in high school, some people see it in other classes along the way, but this is really the first kind of time we run into E, this exponential base. We'll call it the natural base. But anyways, that's a little bit about what that number actually is. You should have a button on your calculator for E. There should be one for just E, and then there should be one for E raised to an exponent because we use it a lot in exponentials. But anyways, let's move on. We're going to use it in compound interest, so what I want to do is just talk through these two formulas. My guess is, again, that you've seen some of this before. Every now and then, this one has a bunch of different letters. So depending on where you've seen it, maybe it's got M's instead of N's. I don't know. There's lots of different ways that you can write this. It's all the same thing. This is for compound interest. So what we're doing is we're trying to track some sort of investment or a loan or something like that as it accumulates interest. And in both of these cases, we've got a bunch of variables that represent a bunch of things. And we've got n in one of them. E here is not a variable. This is that constant 2 point blah, blah, blah. So we've got 4 variables that are shared between both of them. And this fifth one here is only in this first thing. What these stand for, A sometimes we'll call like the annuity. What it is like the end balance. Maybe I'll start down here. T stands for time. We calculate time in years. So when I talk about end balance, it's the balance after this time period has passed. So if we're talking about like T is equal to 3 years, we're looking at an investment over 3 years. We'll say A is going to be the balance at the end of those 3 years after we've put in all the interest. P is the principal. Oops, that's not how you spell principal. There we go. I was in my head because I never remember if it's principal with an AL or principal with an LE. I'm pretty sure it's an AL. I don't know. Doesn't really matter. That's like your initial amount. and R is your interest rate. We got to write this as a decimal. Meaning if we had like 3%, we're going to use 0.03 here. N is the number of compounding periods per year. What that means is, well, here, take this for instance. Most bank accounts, like a savings account that you'd open at your bank, interest is calculated quarterly, meaning 4 times a year you'll get interest on whatever balance you have. So this is the way that my savings account works, where every 3 months I will get a little injection of a small portion of my yearly interest, and it will just add itself to the balance. And if I left that, then what would happen is my balance would grow by a tiny bit, and so then the next time that I would get my portion of the interest, that percentage interest would be calculated on a bit higher balance because I would have the little bit of extra interest from before. So where this new or other compound interest formula came to be is people basically started asking, what happens if we increase the number of compounding periods every year? What happens if instead of compounding interest quarterly, we do it monthly? And in that case, notice up here, we divide our interest rate by n, so we take our total interest rate and we split it up into, if we're doing it monthly, we'd split it up into 12 equal portions, and we'd add that interest in, but then we would do it n times t times, so we do it 12 times a year. So you're adding a smaller amount of interest in more often. And then we said, okay, well, what about if we do it not monthly? What about weekly? So we do this 52 times a year. So now it's a really small portion of the interest being added in every time, but you're adding it in a lot. And then what happens if we do this 365 times a year, every day? Or what happens if we do it every hour, or every minute, or every second? What you'll notice is that you're adding these tiny, 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 tiny portions of our interest rate a whole bunch of times. This is the limit as n is going to infinity, and that's where this limit definition came from. Notice we've got our 1 plus 1 over n raised to the n. There's a couple of variables missing, but it's not too hard to show that if we take a limit of this compound interest formula as n goes to infinity, you'll end up with this. So for this one, maybe I'll do this in blue just to make sure that we can kind of see what's happening. So for this one, the key is we're going to be talking about something being compounded continuously. When we say compounded continuously, it means like we're just always compounding interest. So it's not happening, 12 times a year. It's not happening 50 times a year or 100 times a year. It's happening over and over an infinite number of times. It's just always compounding these tiny little bits of interest. So we'll still use R for our interest rate, T for our time, P is our principal, A is our ending balance, the annuity there, and that should be fine. But now we've got this little constant E. In this class, you're mostly going to be just focusing on this compounded continuously formula. But that's the buzzword you're looking for. Take a look at some examples. What we'll find is that these will not be terribly difficult. Grab your calculator, follow along with these. Let's set them up together, and then you guys can finish them out. Once you get confident, just pause the video and finish out the rest of the example and see how you go. So what I'm going to do is just start labeling things. Here, I've got a 10-year CD. So that's going to be my T. 2.15%. That's my interest rate. Notice it is compounded continuously. That's good. That means we're using that formula with the E. If $10,000 is invested, that's like our initial investment. So that's going to be P. How much will it be worth in 10 years? So what I like to do is just label all of my variables off to the side. So maybe I'll do that in red. I've got A. I'm looking for P. I'm looking for R. And I'm looking for T. A, I don't know what it is. That's what I'm asked to find. How much will it be worth? Capital P, my principal, I'm told that is 10,000. R is my interest rate. It's 2.15%. But I said we have to write this as a decimal, so that's going to be 0.0215. And T is 10, because we're looking at 10 years. Now, just a quick note. If we were told that this was like an 18-month investment, 18 months is a year and a half, so we'd use 1.5 for T. So convert everything over to years when you're looking at that time. But now we can just get our formula and basically do some plug and chug. So A is equal to 10,000 e raised to the 0.0215 times 10. 10,000 still e to the 0.215. If I multiply that stuff out, I have no idea what this is. I've got my calculator. Let me just plug this stuff in. You go ahead and make sure that you can do this too. Make sure that you know where that e functionality is on your calculator, but this doesn't end up being too easy. I don't round things typically until the very end. So what I've got is $12,398 and we'll say 62 cents. I'll round it to 2 decimals because we're talking about dollars and cents. So that is how much this investment, this CD, will be worth in the 10 years. Cool. I could ask you another question. I could say, okay, how much interest did it make? That's a pretty easy question once you've got this number here. It started off as a $10,000 investment, so obviously the interest was $2,398.62. It's the extra bit. So you could say interest is like your ending amount A minus your initial amount P. Easy enough. Again, I suspect that we've got some familiarity with this. Take a second and try this example, and I'll pick it up. We'll see what we can do together, but I guess that you're going to be fine with this. All right, if you've finished this, let's just check it. Notice that this $50,000 is at maturity, meaning at the end. So that's actually A. So we actually don't know P. T is going to be 5 because we're looking at 5 years from now. 6.4%, I'll convert that to a decimal, 0.064. If you mixed up A and P, pause the video again, give it another shot, and you should be able to figure it out. All right, so if this is our formula, we've got 50,000. Is that right? That's the right number of zeros? Yeah. Equals P e to the 5 times 0.064. And now what I might do is say 0.064 times 5. That's going to be 0.32. Is that right? I think so. Yeah. So we've got 50,000 equals P e to the 0.32. This e to the 0.32 bit here, I don't know what that is, but that's just a number. If I want to solve for P, I can divide. So I'll say P is equal to 50,000 divided by e to the 0.32. And now I'll grab my calculator and figure out what that actually is. Let me just make sure I got my order of operations right. I'm looking at 36,307. $36,307.45. We'll say. Let me get that E out of there. There we go. Cool. So that's how much money we would actually have to invest now or pay for this thing now if it's going to be worth $50,000 in 5 years. Neat. All right. Again, these problems I don't think are very difficult. But now we've got to figure out what the heck logarithms are. My guess is that we are less familiar with logarithms in general. They do show up in these types of things. So let's just do a really quick brush up on logs just to make sure we're okay. This is what a logarithm is. This is the definition of a logarithm. So we could say something like, we know that 2 cubed equals 8. It's the same thing to say log base 2 of 8 equals 3. A logarithm always solves for an exponent, you can say. It's trying to figure out what the exponent actually is. Oh no, there's a typo in these notes. This is supposed to say a to the x equals y. Let me scratch this out. This is supposed to say x equals log base a of y. Notice the input of the exponential is now the output of the logarithm, and the output of the exponential is the input of the logarithm. So go ahead and correct that in the definitional logs in your notes if you want. But this is the general gist of it. Now we're looking at exponentials base e. and we want to solve for something like this. Let's just say, look at a real basic one, e to the x equals a. Now, we're going to change this a little bit because we'll have other values in here. But what we can do now is say if we want to solve for x, we could say x equals log base e of a. But log base e gets used so often that we just give it its own name. Call it ln a. The n stands for natural. This is the natural log. We call that number e the exponential base, or sometimes the natural base. So on your calculator, you'll notice right by the e to the x button, you'll have an ln button as well. So we'll use that to solve some things. These logarithms and exponentials are inverses of each other. Which means that they can do some stuff. All right, let's take a look at this example. We'll set everything up, see what's going on. So we have these things here. All right, we want to figure out the interest rate. We're asked about that interest rate. We've got a time limit here, 15 years. And we also have two prices. Notice that the initial payment was $99,000. And after the 15 years, it was sold for $195,000. So let's set up our equation with our little formula. And then when logs show up, we'll use them. 195,000 equals 90,000 times e to the 15r. Cool. If I want to solve for r, I can divide both sides by 90,000. Let's see. 195 over 90. That's going to be like 2 1/6. So that's going to be 13/6. Anyways, you can do that. And now we've got e to the 15r. Now, notice we've got it set up like this, where we have a variable in the exponent, and we've got it equal to something. It's a little bit different because our variable has some other stuff. But what this means is that we can use logs. So what we can do is say, all right, 15r equals the natural log of 13 over 6. And then we could say r is equal to the natural log of 13 over 6 over 15. Which, if we grab our calculator and throw all that in, that divided by 15, we end up with 0.05, we'll just say that. So about 5%. That's approximately the interest rate on the growth of that real estate investment. This works the exact same way if we wanted to solve it for a time instead of rate, because time is also up in the exponent. So let's take a look at an example of that. This one's kind of fun. Here we're looking at how long it's going to take an investment to double its worth if it's invested at 3.25% compounded continuously. So I'll write this out. You guys take a second to think about it. Notice here we're trying to figure out time, and I'll give you this. Sure. All right, but how do we figure out this stuff? Take a second, think about that, and then come back to me. All right, if you've thought about it, what you might notice is that it really doesn't matter what you pick for A and P. All we care about is that it has to double its worth. So sometimes people will say, all right, let's make the principal X, and then A has to be 2X. What you'll notice is that it really doesn't matter. You could have just picked like 10 for your principal and then 20 for A. You could have picked 1,000 for your principal and 2,000 for A. It's all going to end up being the same thing. So let's just do that. Let's pick some numbers, but if you want to use variables, you can. Let's pick like 500 and 1,000. All right, so now when we plug all this in, we've got 1,000 equals 500 e to the 0.0325t. We're going to divide everything by 500. And notice that 1,000 over 500 is 2. All right, so now notice if you had put in x and 2x instead, you would have had 2x over x. You're going to get 2. No matter what you put in here, as long as you're actually doubling here, you're going to end up with 2 on the left side of this equation. So it really doesn't matter what you pick here, which is kind of a cute thing. Anyways, now we can use logs. We can say, all right, now 0.032t equals natural log of 2. And so t is going to be the natural log of 2 over 0.032, which again, I'll have to grab my calculator and see what that is, but let's see. Natural log of 2 divided by 0.032, that looks to me like it's around 21.66. So like 21 and 2/3 years, or you could say like, I don't know, 21 years and 8 months. So that's how long it would take to double your investment at 3.2% compounded continuously. What's cool about this, I think, is that this is the same if you're investing $1 and trying to grow it to $2, or if you're investing $1 million and trying to double it up to $2 million. It doesn't really matter what you're starting with. It's going to take the same amount of time at that fixed interest rate. Anyways, that's all we've got for this. Again, I expect that a lot of this is a bit review. Jump into some of these problems and see if any of them give you trouble. But for the most part, we just have to remember where these logarithms show up and where they don't.